I used the campus information system, Canvas, essentially, that can send the whole class an email at once. I don't know if everybody saw it. It was, was that yesterday or the day before? I think it was just yesterday. Anyway, it's for your reference, so if you haven't seen it, it's concerning the clickers registration. I went ahead after we did it Monday, then I could more easily see, it tells me who and who does not have an active license, whether you've purchased one or not, or whether you actually went through Canvas modules to create your account. If not, it tells you to go back and do that to link it. Anyway, the email should explain it if you're sitting there going, huh? And it lists those. We'll try it again today, but I'd like you to look at that, and it gives you the things to try if you're on one of those names. Interestingly enough, there were a handful of you that it lists you have an inactive license. I called WebAssign on this, yet I'm still getting your data. Actually, I'm getting everybody's data that responds, but I can tell it's your data. They're confused about that themselves, so they're going to get back to me. Long story short, look at the email, see if it applies to you. Even if there's any doubt at all, just go back and redo it. Doesn't hurt. If you've already created an account, that's okay. You just follow the modules link and re-log in. And bottom line, if you're here responding, I'm getting your answers. I have them, even past ones. So once we link you up with your data, I'll have everything. It's not like we're losing it, so you know. On that, I also want to remind folks that WebAssign gave you free access for a while. It's nearing its completion. Thus, you will need to purchase that to continue using it the rest of the semester shortly. What were there, like 5 or 6 days left or something like that? Calendar. Where are we at? Here we are, Wednesday. Continuing chapter 3 and starting chapter 4. We'll finish chapter 4 this week. Oh, right. And you've had open your next homework on chapter 3, which will be ultimately due Sunday night, in case you were not paying attention. Do you have any questions? How many have read the superhero paper stuff? Most of you have not yet. That's due anytime up until the due date, which is in a couple months. But all the instructions are there. I thought this might be long enough to go over. But the gist is, briefly then, you get to design your own superhero. Whether it's a hero or a villain, you're going to choose one fundamental physics principle that we cover or not. Even if we don't cover it in class or haven't gotten to it yet, or you just like one I'm not discussing, that's fine. You can use it. You'll just use that physics to explain your superhero. And your hero can either abide by the laws of physics or not, or a combination, as long as you use physics to explain why. It's not that long. It walks out everything that's included. So if you haven't, and you got plenty of time, obviously, but that's what it's about. Well, I chose 4 questions for us on inertia to see how we're doing with this. So let's do it. It's coming up. So you can see the channel is still 41 for your clickers and the session ID for ResponseWare. A couple of you mentioned last time that your username, as you were logging into ResponseWare for the first time, it should save that data, but the first time, I looked in my turning account, and my username was whatever I entered when I created the account. It just says Adam Beehler. It doesn't necessarily have to be your UID, unless that's what you put in. Thus, if you're having trouble logging into ResponseWare, you can log in online to your turning account and remind yourself what your username was, if you haven't already. All right, polling is open. Which one of these is not a vector? Remember, a scalar just has magnitude. A vector has magnitude and direction. So which one of those does not have direction? Excuse me. So I see the responses are slowing down. 10, 9. Holler if, when I start counting, that's your clue, so you have an idea, and if you're still thinking, you can get your answer in. But also holler if, like, you're having technical difficulties. I might be able to pause. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So most of you were speed, but several of you thought speed was as well. Does speed have a direction? Well, those of you that just vocalized, you answered A. I bet the ones that answered D didn't vocalize. Speed is just a magnitude. It's just a scalar. So that, whoops, wrong button, is the one that's not a vector. So when we just talk about speed, it's just the magnitude of the velocity. All right. Oh, that's not the one I want. This one is. All right, go. A space probe in remote outer space continues moving. Why? Not exactly why, but which one of those? So quiet. You guys can talk to each other, help each other out with these if you want. I don't mind. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you C. That's correct. If you chose A, that's Newton's first law. Things in motion will stay in motion because of their inertia. And inertia is not a force. It's just this property of matter that resists changing. We just call that resistance to changing inertia. So if it's moving, it'll just keep moving. Why would it change? Yeah, only if something acts on it, you apply a force to it to change that. But that can seem counterintuitive in our world where it seems like everything slows down or ends up stopping somewhere. But that's because there's always forces on it. Gravity, friction, air resistance. You remove those, it just keeps going. Does that make sense? Any questions, concerns? All right, polling's open. When a 10-Newton object is suspended at rest by 2 vertical strands of rope, what's the tension in each rope? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Overwhelming B. Woo! Yeah, 5 newtons. How could that ever be different? Let's say you're hanging from 2 rings, like your homework problem. Could it ever not be 5? Yes. Tilted or uneven, kind of like this. And what if I was hanging from 2 rings, but I'm over here? What's your gut tell you? How they differ? Yeah, this one is holding me more up than this one is, isn't it? Yeah, so the tension would be greater here than here. What would the 2 tensions sum up to, though? Yeah, they still have to equal 10 because the total up is balancing the total down if you're at rest. Good, and you can shift this way. Yeah. Good. One more. Well, if you were paying attention, I just accidentally showed you the answer, but anyway, go ahead. That's a little sigma. I don't know if I did that in this class yet. Summing up all the forces. That sigma there means adding up all the forces. So in other words, if the net force is 0. May I borrow your pen? Choose the slide to go to that doesn't have the answer. Hurry up. 5, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you see. Correct. If the net force is 0, then it's not accelerating. If it's not accelerating, it's not what? Changing. And changing what? Its velocity. So it's staying at rest or it's continuing moving at that constant velocity. And we call that equilibrium. If it's at rest, it's static equilibrium. If it's moving at a constant velocity, it's dynamic equilibrium. Okay. There we have it. You can put those away. That's mostly how I use these. Kind of after we've covered it, it's a way to gauge how well you're thinking. And for you, this is, if you did well, feel good. If you didn't, you know what to review. And of course, if you're confused right now, ask me while you have me.
So acceleration refers to a change in velocity, not just speeding up, but it could also mean slowing down.
That is correct. Acceleration is a change in velocity. Velocity is a vector, magnitude or speed. So if its speed is changing,
Or direction.
yeah. So if it's changing its speed, it's accelerating. But its speed could remain constant while its direction's changing. Thus, its velocity is still changing, and there's an acceleration.
Okay, but it doesn't, because in the sort of normal world, I guess.
Yeah, we use speed.
Non-physics world.
Non-physics
accelerating
length.
means going faster, it doesn't mean slowing down.
Yeah, accelerating means just speeding up. We would then say acceleration and deceleration.
Right.
Yeah, to clarify, in physics, acceleration means you're changing your velocity, period. Whether that's speeding up, slowing down, or changing direction.
That acceleration then would be figured as negative.
Which acceleration could be positive or negative because it's a vector. And that sign will tell you which direction it's changing. And or speeding up, slowing down. Yeah. Good. Anything else? All right. We had distance equals rate times time. Some people think that. So velocity is distance over time. It's your change in position as your time changes. Acceleration was a change in velocity. You can also rewrite that and think of that as velocity is acceleration times time. Now I pause because for those of you that are scribbling this down, I know how it is. When you're writing down, it's harder to pay attention. I like this one because, let's see. What if you started not moving, and then you accelerate for a certain amount of time, you now get up to a certain velocity. That tells you how it changed. Do you see that? So you can even rewrite this one more complete. The final velocity is the initial velocity, however fast you were going to begin with, plus that change. Because that is essentially the change in the velocity. Let me get on this side. So if you want to know how fast you're going after you accelerate for a certain amount of time, just add that change to however fast you were going in the first place. That one's useful. They use that in every physics class, not just this one. And then we had that other one where that was distance is 1/2 AT squared. That's how we'll use it in here. But you guys can handle this. Let's say it's the final position. You want to know where you end up? Well, depends on where you started, your initial position at some distance x from a reference point. If you go a constant velocity, how much farther will you go? How will your position change if you go a constant velocity? Well, it's right there. How far do you go if you go a constant velocity? Vt. So if you're at a certain spot and you now go a certain velocity for a certain amount of time, you'll end up somewhere else. What if you accelerate? Say you're already moving, you're there, and now you accelerate. How far do you go? That tells you how your position changes with the acceleration. In advanced physics classes, they use all of this. But you have it all. We just usually break them down into parts. But this is a powerful equation. You can shoot a ball, and I want to know where it lands. Well, I've changed vertical height. I've changed horizontal height. Took a certain amount of time. There's gravity accelerating it down. I shot it yay fast. You can just plug all that in there, I started here. I shot it that fast. Gravity is how it's accelerating. And you know exactly where you end up. It's powerful.
So what does the X stand for?
X for position. For example, you know, if you have your X and Y axes, and here's the origin at 0, 0. You know, say you started here, and you have a velocity going that way. You'll end up over here somewhere at XF. So I'm just using X generically for representing a position. It would work the same. You could make it a Y when you're changing vertical distance. Again, this isn't to scare you, but you guys, you know everything now. Some of you might go on, take another physics class. So this one's fun when you're dropping things, because we know what that is, so you know how deep it was. You can throw things up, too. Let's see. Just my counting's not exact, but the idea is, how long does it take to go up and back down? 1001, 1002. You know, it's about a second up and a second down. If I knew how fast I threw it, I could add that in with that time and gravity, and I know exactly how high up it went. I'm not going to ask you to do it. I just want you to realize it. And physicists, scientists use that all the time to define something's motion. How fast will it be going at this point? Where will it be, yay, time later? How fast do I need to shoot this so that, you know, firemen don't do this, but trust me, some scientists figured it out. Based on the pressure of the water hose, the water comes out at a certain velocity. If they have to get it up into a 10-story window, is that enough velocity to make it? Maybe we need more pressure. You can do things like that. Just thought I'd kind of review all those formulas, lest it seem confuzzled in your brains. Friction. I want to do a little more with friction. So we keep mentioning that. There's two types of friction. Static friction, and the other one's called kinetic friction. This one is obviously not moving. This one is. They can have different values. And let's see if I can demonstrate that. So this is a fish scale. It can measure the force. So for example, if gravity pulls down on this block, then its mass is being accelerated down and there we go. And what do we get? About 9 newtons. 9 newtons. Okay, I'm going to pause. Earth pulls on this with 9 newtons of force. That's its weight. What's its mass? Can you calculate that? What would we do? You had to do it for your homework, so I know most of you figured it out.
Just solve for the mass and force per mass.
Yeah. This equation tells the relationship between force and mass. It's Newton's second law. What's the acceleration here? Yeah, gravity, so it's about 10 meters per second squared. What was the force? 9 newtons, the standard unit. That means if you use mass in kilograms, the standard unit, and the acceleration in meters per second squared, the standard unit, you get a Newton. So what would the mass be? Nine divided by 10. You divide the 10 over, or yeah, 0.9 kilograms. There you go. The block weighs 0.9 kilograms, or 900 grams. Now help me, are you just, it's the middle of the week humdrum stuff, or is this confusing? Because I'm not getting as much response. Is this okay? Give me something. All right. So it's more like a duh, we got it, move on. Okay. Well, that force pushes down on the surface. The surface is pushing up with what force? 9 newtons, because it's not moving. They're balanced up and down. The support force, the normal force, balances its weight. It's in static equilibrium. The net force is 0. I'm going to make it even more. Let's not do that first. So if I pull on this, it's not moving. Oh, there, and it starts to move around 3 newtons. Let's see again. Pull slowly. I can increase the force, oh, there, and about 3 it starts to move. That's the static friction. In this case, for these materials, I need 3 newtons of force to start moving this. What do you think will happen if I put the lead brick on it? Yeah, it should take more. Let's see. Oh, we're already past 3. Notice I keep pulling. See, right now I'm pulling with 6 newtons of force. What's the block pulling back with? 6. Because it's not moving. The net force has to be 0. So the force I'm pulling has to be the same it's holding back. That's the static friction. The static frictional force right now is 6 newtons. What is it now? Yeah, it can change. Keep going, keep going, keep going. Oh, there we go. What did it get up to? 11. So the static friction force increased to 11 newtons. But once I exceeded that, got to that or exceeded, did you see it drop back down? Let's see, to keep it moving, or get it moving, we get up there, oh, 12. But now, to keep it moving at a constant velocity, it only needs 10. If it's at a constant velocity, are we in equilibrium? Yes. Constant velocity, not changing. Acceleration then is 0. That's the kinetic friction. Was like the 10 newtons. This is generally always less than that. It's harder to get something moving, overcome the static friction. Once you do, you can keep it moving with less force at a constant velocity. That's the difference between these two. Hopefully that helps. You can see too, friction has to do with the normal force. How much this surface pushes back up on it. By increasing the normal force, the friction went up. I think this is my favorite way to show it. Phone books. Anybody tried this? Becoming more popular as people learn about it. So I just took 2 phone books and interwove the pages together. There's no glue. There's no adhesion here. I just taped them. I did tape the outside cover, one little piece of Scotch tape, just so it doesn't like unravel. So I just interwove them like this every other page. It took a couple movies. The first time it came out all cattywampus, so I redid it. But so the idea is there's some friction between the pages' surfaces. I will watch another movie if somebody can pull this apart. Maybe we can get 2 volunteers. Want to play tug of war? The goal is pull this apart. Come on down. It's fun. Come on. Where else do you get to have fun in class? You know what happens? Well, that's okay, even if you do. Well, it's not as impressive, me just going, come on. Come on down. Thanks. You want to help too? All right, come on down. So I put these wood handles on here just so I could clamp onto it. It's hard to hold on to the phone book, so I did drill holes through the ends here so you had handles. Mythbusters did this too. They have an episode on it. All right, separate it. Come on. We got him. Yeah, we can't do it. Thank you for coming and helping. Yeah, Mythbusters did this. They actually got up to where they had two vehicles trying to pull it apart. Anybody seen that episode? What happened?
I don't remember how it ended, but I just remember they got up to using like 2 tanks or something like that.
Yeah, I think one of them was a really big thing, if not a tank, I remember. They did actually come apart, but not here. It actually ripped where it was holding it. So the pages were still actually holding it. That's a lot of friction. I've hung from this, swung, use these pulleys that are holding up this demonstration right now. So I just raised it up and hung from it, and swung from it. It was all good. How many have seen these finger cuffs? You like squish it and put your fingers in. And then the idea is, you can't get them out. That's how that one works. It's a misconception. It's not because there's a whole lot of surface area now. That's less important. It's actually pretty negligible. It's because as you pull them apart, what's this cuff trying to do? Stretch. And can you see the middle part? I know it's small. It gets skinnier. It's squeezing harder on my fingers. The more it squeezes, the more the normal force increases, that support force. And that increases friction enough that you can't pull it out. You can break this, that's for sure. But how you get out is you scrunch it back together so that you can. Because if you do it by yourself, nope, hold it. There we go. It's like a deck of cards. You could do this yourself with the phone book. The idea is if you shuffle a deck of cards, it's a piece of cake to pull them apart like this. I'm not squeezing them. But if you squeeze this one, it's forcing them together a little more. The normal force increased, so did the friction. It's a lot harder. If you think I'm faking, you can come try it. So, 2 types of friction. Static friction is always greater than or equal to the kinetic friction. Mass versus weight. That's what I want to do. What would you guys say? What's the difference between mass and weight? Because people in the normal world use those interchangeably. They are not the same thing. Court.
Mass is never changes in an object. Well, it can change, but if you have an object like this block, in space it's going to have the same mass, whereas weight is weightless because there's no gravity pulling down.
I like that. He says, yeah, the mass doesn't change. You take it out into space, this will have the same mass. But its weight would be different. Anybody want to add to that? Tina?
Mass is like, has to do with its inertia?
It does. Mass has to do with its inertia. So does its inertia change?
No.
If we took this to the moon, would it have the same inertia? That's correct.
Weight is its mass.
There you go. Weight is a force. It's mass that's being accelerated due to some massive body like here on Earth. If you went to the moon, how does G change? It's less. There's less acceleration due to the gravity of the moon because it's not as big. It's about 1/6 less. So you weigh 1/6 less on the moon. That's weight. Is your mass the same on the moon? Yeah, that's the difference. And I like that, Tina, you brought up that inertia concept. That's how I do this. Here's a flimsy little piece of string. This lead brick weighs about 13 pounds. So it's got a fair amount of inertia. Do you think, I have to pull it just like this, there's friction there, but I'm also have to overcome its inertia. I'll increase the force and increase until it moves. Do you think the string will break before I get to that force or not? Yeah, that could be fun. Let's do it that way. I just thought of this. I'm going to tie a knot, and let's watch the force change. All right. Oh, there we go. So the string can handle that force. That overcame the static friction. What if I pull it faster? Why the difference? This could handle the force it needed to move it. What'd you say? Kinetic friction. That one actually broke before it even moved. It had to have been more force when I jerked it than the string could handle. But how come it requires more force when I'm trying to move it fast than when I do it slowly? It's the inertia. I do this to emphasize that difference between mass and inertia and weight. The weight is determining the friction. This pushes down with its weight, so the normal force is the same because it's not moving up and down. And that determines the amount of friction you got to overcome. But inertia is based on its mass. And it really has a lot of it, and it wants to resist moving. So things at rest want to stay at rest. So yeah, you can ease into it, but yeah, when you jerk. You guys probably experience this every day with your toilet paper roll. When's it most like, you remember you're pulling the paper off the roll, and it breaks. Oh, I wanted more. You pull, no! Or at some other point, you pull on it, and it just keeps unrolling. When do the two happen? There's a pattern. When does it normally break on you prematurely? If you pull fast, yeah, you can do that. Same idea. Or when it's bigger, newer. It's got more inertia when it's bigger. When it's smaller, often you do a little yank and the thing's like, same idea. So, next time you're doing your business, you can think about inertia. Or not. Now, I mentioned this with the wheel. A lot of people don't get this. When a wheel rolls like this, if it's trying to go this way, the car's going this way, the bicycle's going this way, if it rolls, which way is the frictional force right here? Point. Most of you are pointing that way. Which way is the wheel trying to move at the surface? Yeah, the wheel's trying to move that way, isn't it? Let's pause. Which way is this trying to move? Yeah, that way, because I'm trying to move it that way. So friction's always opposite the direction of motion or intended motion. I'm intending it to move to your left, so friction's to the right. Even while it's moving, I am pulling it to your left, so friction is to the right. Same thing with this. The wheel right down there is trying to go that way, so friction opposes it and actually pushes the wheel that way. The only force on this wheel, when I let go of it, is friction. Why does the wheel go that way? There must be a force on it, right, to move it that way. Think of it, you're on your bicycle and you hit the pedals are connected through the gears and the chain, and it turns the wheel tries to turn. It's trying to turn on the ground like this. Which way is friction? Yeah, it's that way. That's why your bicycle goes that way. It's that frictional force of the ground pushing back on your bicycle to accelerate you. Counterintuitive, but does it make sense now? That's friction. Think of a world without friction. Completely remove friction. What would be different? Nothing would stop. Good. Nothing would get started either. What else? It's kind of a fun game to play. I play it often. But yeah, you'd have no traction. You couldn't walk. This wouldn't work. Which way is friction on my feet when I walk this way? Oh, we got mixed results. Right? How about when I go this way? Which way is friction? Let's look at my foot. My foot's trying to do this, right? Foot's trying to go that way. So what does the table do? Yeah. Your shortcut answer is, if I'm walking that way, there must be a force propelling me that way. That's friction. But if you get rid of friction, you couldn't walk. We wouldn't go anywhere. We might need some thrust or something, propulsion or something. Do you think
Friction is in the direction that you're moving.
Friction's always opposing motion, the direction of motion, or intended motion? Because static friction is nothing's moving,
Right.
but it's trying to move a certain way, so it opposes that. How about you wouldn't be able to write either? You know, your pencil and pen, they work because of friction between the surfaces. World would be a lot different place without friction. So even though it hinders us and makes us use more energy, at least we can do it. I think we've covered everything in chapter. I got these out of order. 3 and maybe even 4 at this point. Let's do some examples. I'm ahead of schedule. You guys have asked good questions, so it's worked out. Let's see if these two work today. It's always fun when you can have dart guns in class. So I compress a spring. This one has clay on it. In theory, these springs are fairly identical, so I've stored the same amount of energy in these. They're going to exert the same force on each dart. Because they're the same spring, compressed the same amount. So they'll push on each dart the same amount. Which one will go higher? The one without the clay? Absolutely. The one without the clay will hit the ceiling. Why? Yeah. So if we take this equation, the force was the same. So the one with less mass had more acceleration. And the one with more mass had less acceleration. This one changed its velocity more and got shot up faster, so it hit the ceiling. The one without the clay. Again, that's Newton's second law. Look at it this way again, one more time. Acceleration is proportional, this often means proportional, to force. As force gets bigger, the change is greater. We say this is inversely proportional. Because as the mass gets bigger, there's more inertia and resistance, it doesn't change as much. And Newton's second law just puts those together. That relationship to guide our thinking. And that explained what was going to happen with the darts. Yeah. All right, let's go back to the rock and the feather. You drop them, they fall. There's forces on them. What happens when you drop them? They fall to the ground under the influence of gravity. Do they hit at the same time? No, because of air resistance. Yeah. Do a little free body diagram. On this one, there's the force down. It's weight. The force up, air resistance. The way I drew these, probably shouldn't have done that. If this one's bigger than that one, it falls. The net force is down. You add this plus that. One's positive, one's negative, so there's a difference. How should I draw the forces on the feather? Larger air resistance. And how should I draw its weight? Should it be bigger than this? So if it was less, like this, what's the net force? Which direction? Yeah, this would be going up. So it needs to be bigger than that, right? So we could do that. Now this would go down. Let's compare, though, this force to this force. What's wrong? These represent their weights. Which one should be bigger? Yeah, so I need to fix this. Different mg. So that's good. So we have a weight down on the ball, but again, it weighs more than the feather. There's more air resistance on the feather, but in both cases, this is bigger than that because it falls. And this is bigger than that. It falls. The net force is down for both. And again, what's the same for both of them? Acceleration. So the one with a lot of mass and the little feather. Who needs more force? Yeah, the larger rock. And it does. It weighs more. So again, I'm just reemphasizing, things don't feel the same force when they fall. That's not why they hit the ground at the same time, ignoring air resistance. It's because they accelerate at the same rate. So if the acceleration is staying constant, you look at these ratios. If the force is constant, you look at those products. You can apply Newton's law in either way, depending on your situation. I'm done. Questions?
So F equals mg is force equals mass
Times the acceleration due to gravity, so we call it g. Thanks.